Hi everybody, we are moving on to the different types of rigid motions. This is Miss Osier.
And Miss Perrier.
And let's get started. So for a rigid motion, it is something that stays congruent. So it stays the same shape and the same size after it's been transformed. Okay, that means the distance between the points are preserved. It means that if my arm was 4 feet to start with, my arm is still 4 feet after I've translated or dilated, or, well, not dilated, or reflected or rotated. Okay, so those are the three that are rigid motions, the ones that stay the same size. Which one's not a rigid motion then? Sorry, that's me just showing them all.
Dilation is the one that is not a rigid motion because it does not preserve shape or size. We know that with dilation, all you have to do is multiply, so it's either getting bigger or it's going to get smaller. Therefore, it is not a rigid motion.
So isometries and direct isometries. Isometries is a synonym. It's another word for rigid motion. So you're going to get all of those again. Now, a direct isometry means not only is it a rigid motion, but it also maintains its orientation. So it keeps the orientation the same. That's only going to be a rotation and a translation. You should know by the time you watch this video that reflection does not preserve orientation. So that is not a direct isometry.
So our first one that we're going to talk about is translations. And translations, all you are doing is just taking your point and sliding it somewhere else on the coordinate grid, as you can see with the square there. And remember, first you need to go left to right first, then you need to go up and down. So as you can see with A here, we did 3, 4. So all we did was go 3 to the right and 4 up. And for B, we did -3, -4. So we went 3 to the left and 4 down.
Okay, so a fast way to do this, if you wanted a shortcut, you also just need to realize that it's just adding. So you take your point, -5, and you add the 3 because it's positive, or you take the point 2 from, again, I'm going from here, 2 plus, and then it would be -4, so 2 minus 4 to get -2, -2. So you can either physically move it as we showed in the previous slide, or you can just do the shortcut. Okay, number 2, when the transformation is performed, the image is A prime, -3, 4. So this is asking you to go backwards. So this is similar to what we did in the first worksheet where you were given B prime and you had to get B. Same thing. So it's saying what plus 2 gave you -3, what minus 1 gave you 4. And you just work backwards through it to solve for -5, 5. In number 3, they're not telling you the rule, they're making you figure it out. They're giving you the image and pre-image pair. So you started at 3, you went to 6. Well, if I started at 3 and went to 6, that would have been a movement of right 3. And then I started at 5 and went to 1, that's a movement of down 4 or -4, as you can see in the red there. So if I do the same thing to the point they gave me, well, there's my new point, 0, -9. And the last one on this is the image of 3, -4 under that translation. So again, if I do the shortcut, 3 minus 2 is 1, -4 plus 0 is -4. And that's it for translations. They are pretty straightforward. You're just sliding left, right, up, and down.
The next one we're going to talk about is rotations, and all rotations is you are going to be turning the point to the left every turn for every 90 degrees. So we have 4 quadrants, so that's how we will deal with that. So you can either do it one way where you physically turn your paper to the left to find that, or there are 3 separate rules that you will need to remember if you choose to do so. And they are right there. When you rotate 90, you swap and you change Y, which of those some swap just means flip Y and X, and change just means negate, which is if it's positive, you turn it to negative, and if it's negative, you turn it to positive. Rotate 180 is just changing them, so if they're negative, make them positive, and if they're positive, you make them negative. And then rotation 270 is swap and change X. And again, swap just means we change where X and Y are, and change just means if they're negative, make them positive, and if they're positive, make them negative.
So now we're going to do a few examples. We're going to do them the actual physical way. So if you want to do it the physical way, you're going to plot your point. So in this case, -3, 4, and you're going to put an arrow in the top left corner because we always rotate to the left. So we actually physically do that. So you turn your paper left 1 turn. Now, based on where I'm currently located, my point would be at -4, -3. So that's how I get my answer. It's -4, -3. Now, if you're doing this the rule way, you know that you swap them, so 4 and -3, and then you change what was the y, so now that +4 becomes a -4. Either way you want to do it, but you're not given those rules.
Yeah. Okay. Next, we're going to rotate 180 degrees in the clockwise direction. So counterclockwise here and clockwise here are the same thing. It is the same rule here. So if you want to turn your paper, you turn it twice, and that's what will be your new point. If your new point would be 2, -1. And then that is if you do it the physical way. If you want to do it the rule way, all you do is just change the signs of -2 and 1, where it would still be +2, -1.
All right, number 3, we're going to rotate 270 degrees about the origin. About the origin means do it the way that you've been doing it. That's called a center of rotation. We're going to talk about when that changes, but this rule applies for when the origin, meaning 0, 0, is your center. So again, I'm going to turn it 1, 2, 3 times because it was 270. My point now lies at -1, -5 because of the way it's currently oriented. If I wanted to do it the rule way, I swap my x and y, and I change the sign of the original x. So -1, 5, and then the 5 changes to a -5.
Next one, we are rotating the point 2, -3 over 90 degrees clockwise about the origin. So all that means is if when you rotate it clockwise, you're going to have to turn your paper to the right here. So we turn that once, and you see our new point will be -3, -2. But if you want to do it the rule way, this is just another thing to think about. Rotating it 90 degrees clockwise is the same as rotating 270 degrees counterclockwise. So if you want to remember that, that's how you would do it. It's the same exact rule, but again, that is all up to you.
All right, number 5, now we're going to a different center of rotation. So now is where it gets a little bit trickier. So step 1, we plot the point A. So A is what's plotted in red. That's at 1, -3. We're rotating 90 degrees about point B. So this is where it changes just a little bit. We have to also plot that point, 2, -2. Now my suggestion is always to label your point A. In my case, it's the red one, so I can clearly know which one I'm talking about. And then circle your center. In my case, it's the blue one, so I know which one it is. You want to make sure you remember where the center is. Okay. Reason being, we're going to rotate now as we usually would to the left 1 turn. There I go. Instead of counting where you are from the origin, you count where you are from the center of rotation. So from the center of rotation, from the blue dot, I have to go down 1, right 1 to get to the red dot. So then I put my paper back, and I do exactly what I just said. I go down 1 and right 1 from that center of rotation, the blue dot in my case, and I end up at 3, -3. So it's a little bit different than before, but it's still the same thing as far as rotating your paper and figuring out where you would be. You just, instead of being at 0, 0 to start, you're changing your 0, 0 to that center of rotation. So here's another example with that. So -3, +2, about point D, which is at 0, 1. So again, we rotate our paper 1 turns, 2 turns to the left, so we're upside down essentially. From the blue dot, I have to go down 1 and right 3 to get to the red. So I just remember down 1, right 3. Maybe I write it down to the side. I put my paper back. I go to the blue because the blue is my center. I don't go to the red. That's a big mistake people make. I go to the center of rotation. I go down 1, right 3, and I know that that is my image at 3, 0. So that's how to rotate off a point other than the origin, and that does take some getting used to.
Our next one that we're going to talk about is reflection, and reflection is just flipping your image, your pre-image, over a specific line. So here is a bunch of our rules. So reflection of the x-axis, all you're doing is changing y. So if it's positive, you make it negative, and if it's negative, you make it positive. Reflection of the y-axis, you're just flipping it over that line. You can either count the boxes or remember this rule. You're changing x, so you're going to make it positive, make it negative, and if it's negative, make it positive. Reflection over the line y equals x, you can see that right there. And all you're going to do for that one is swap x and y, so you're going to change where they are, change their positions. And then the last one is reflection over the line y equals negative x, so it's just the opposite line. And for that one, you're going to swap and change x and y. You're going to change both, not just one. You're going to change both.
Now, as far as all of these rules go, if you're not a rule memorizer, you can always physically do them. The only two we suggest you do memorize are those two, because the physical way of doing it, it just takes longer. You have to remember where those lines y equals x and y equals negative x are. We just really encourage you to memorize those two rules versus all of them, because you could just physically do the rest if you don't want to memorize. All right, so here's some examples. We're reflecting over the x-axis. So if you're doing the rules, you already know that it's going to be 3, 2 because you change your y. However, if you want to count, you count up 2 to your x-axis and then up 2 again from the x-axis, and you still end up at 3, 2.
Same one here, we got our -1, -4, and we're transforming it over the y-axis. So again, if you prefer to count the boxes up to the y-axis and count how many over, that's totally fine. But if you remember the rule, all you got to do is change x. So our new point would be 1, -4.
Going over the line y equals x, again, if you wanted to physically do it, this is what that would look like. But I find it much easier to just memorize this one. We swap x and y. So 2, -3 becomes -3, 2. They just swap positions.
And the next one, it's y equals -x here. Remember that there is that little negative there. So there it is physically. So the rule is we're going to swap and change x and y. So you can't make a 0 negative. So it stays the same, but your positive 4 will become negative. So our new point will be 0, -4.
Now, sometimes they ask you to reflect over lines that aren't those 4 main ones. And when that happens, you simply graph the line and count to it. There are other algebraic ways of doing it, but the physical way is what we're going to talk about right now. So x equals 3. You need to go to the x-axis, find where it equals 3, and it's actually a vertical line, just as a reminder from what you did in algebra. That's going to be a vertical line. So you can see that my red point is currently 2 away from that purple line. And then I go 2 away in the other direction, and I know that my point is now at 1, 1. I almost said 1, 5. 1, 1. Okay.
And then for the last one, we're going to reflect it over the line y equals -2. So again, you can just plot that. But as you can see, our point already lies on that. So therefore, it isn't going to change. So it is invariant. So our position of our point does not change at all.
Okay, and that's it for this video. We know it was a little bit longer, but that covers a whole lot of content. We will see you in class. Have a great day.